Hi, this is Remembering the Past, the show where we talk about people who died recently who've had a profound effect on our history, our society, or our culture. And tonight, in our ongoing series on Nobel Prize winners, we're going to talk about Sir Harold Kroto, who died recently at the age of 76. Dr. Kroto shared the 1996 Nobel Prize in Chemistry with Dr. Richard Smalley and Dr. Robert Curl for their discovery of a new carbon arrangement known as the buckyball. It was sort of a geodesic dome of carbon, and it was known as the buckyball because it was named after Buckminster Fuller. It had 60 atoms of carbon, and it was basically an interlocking series of hexagons and pentagons. Here's a brief report on Dr. Kroto and the buckyball C60.
The universe consists of a few key elements. Carbon is one and is fundamental to life. We used to think it existed only in two forms, extremely hard, diamond, the other extremely soft, graphite. Then, in 1985, a scientist named Harold Kroto was looking into space for a molecule called HC7N. As he and his colleagues were trying to recreate HC7N inside the lab, they discovered something amazing. A pure carbon molecule made up of 60 carbon atoms and nothing else. It was shaped like the geodesic sphere an architect named R. Buckminster Fuller designed 40 years prior. So Kroto's team named the molecule Buckminster Fullerene, commonly known as buckyball. Kroto's discovery won him and his team the Nobel Prize and led to the science of fullerenes, which has applications such as solar cells, nanocircuits, drug delivery systems, and carbon nanotubes. Sir Harold's journey proved that sometimes looking out into the universe can open our eyes to worlds right in front of us.
Dr. Kroto was born in England, went to Berlin when he was a young boy during the war, and then went back to England and grew up in Bolton. He got his postgraduate degree in the United States before he went back to England. He was quite an articulate guy, and he liked to talk about his work, and here he talks about the perfect structure of C60, the buckyball.
Yeah, I guess it is perfect because C60 is a pure carbon molecule, whereas diamond and graphite have got to have dangling bonds on the surface and on the edges. But I think it really was on a Tuesday morning. On the Monday, we had discussed what it might be, and we discussed Buckminster Fuller's domes, that maybe this carbon molecule, which was seen to have great strength, was a sphere, that it was related, and I had a star dome back home in England. And we went out to a restaurant that evening, and I remember describing the star dome had not just hexagons but also pentagons. I was thinking of calling my wife up, asking to find this model of the star dome that I had to see whether it has 60 vertices. But I didn't do that. But that night, Rick cut out hexagons and tried to make it, and couldn't make it. And then he remembered I'd said that I think this structure had pentagons. And when he put the pentagons, it magically curled up, and the next morning came in with this beautiful, wonderful little paper ball. And I think we were all totally ecstatic and realized that this was something special. A little bit later, I started to have the odd question mark because half a dozen papers came out just after ours to say we were wrong. But then I, playing around with little modeling kits, and realized if 60 was the right answer, then 70, which is an unusual number, should be the next favored structure. And I call it sort of like Don Quixote and Sancho Panza, or Batman and Robin, or the Lone Ranger and Tonto. And in fact, that turned out to be correct. So it was ecstatic the day of realizing what it might be, and then a few months later realizing that if 70 was also strong and a favored feature, then it must be correct.
In a Nobel Prize interview, Dr. Kroto discusses the evolution of his work, his partnership with Dr. Smalley and Curl at Rice University in Houston, and how a half-price bookstore in Houston helped him win the Nobel Prize.
The period from about 1974 to 1978, that 4-year period, where my work in carbon phosphorus and carbon sulfur chemistry was really, really very exciting. We'd go in almost every week or every 3 weeks to a month, we'd have a new, really quite significant result. And then in 1975 and 1976 and 1977, we detected the carbon chains molecule. So that period was, for me, a golden period. I didn't realize it was a golden period, but in retrospect, it was a time of something special. The carbon chains were there, and they presented a bit of a problem because they didn't quite fit with the accepted theories of the way molecules were forming in the interstellar medium. It seemed to me they were actually produced in stars, or cool stars, stars with high carbon content, and were being blown into the interstellar medium. So there are stars which, as they use up the hydrogen to form helium, they then go on to a second phase. They use up the helium to form carbon. At a certain stage, they tend to explode and blow the carbon and other elements off into the interstellar medium. But they must be at moderately high pressure and temperature, and it seemed to me that there were going to be conditions in some of these stars, if not all of them, in which carbon chains would form. And therefore, what we were seeing was the debris that was being blown out to the stars. Now, that might or might not still be true. I mean, I don't know. So I thought this was an interesting idea, and I would go to conferences and suggest there's a third way of making these. They're coming from the stars. And in fact, a star was detected which showed these things blowing and blown out. But it's still, no one was really paying any attention to it. Then in quite a long time after these discoveries, 4 years or so after the last of those, in 79 or so, I was in Rice University, and Rick Smalley had developed this fantastic apparatus in which you take a laser to vaporize graphite. And Bob Curl, whom I was visiting, suggested that I go and see him because he'd made this beautiful result on silicon carbide and shown that silicon carbon, was a triangular molecule. And I thought it was really, really interesting. As I was talking to Rick and watching him jumping all over this fantastic apparatus, because he's a very ebullient and forceful character, I thought, well, maybe if we vaporize graphite, we'll produce the carbon chains. We'll simulate the conditions in a carbon star. We'll get a plasma which is similar to the plasma in the sort of intermediate atmosphere of the star. That was a simple idea which could have been done almost on the spot. And there are other ramifications. Anyway, I suggested it to Bob Curl, and Bob Curl rang me up, and sometime about 16 months later, because, it wasn't an experiment that I was rushing around to do. It was an interesting experiment to me. It was less interesting to Rick, but Bob was pretty keen on one aspect of this experiment, and I was keen on another, very simple, but also both aspects of it. And so in 1985, I got a phone call to go to Rice, either to go to Rice or, in fact, just should we send you the results when we get them? Here I made a very important decision. I actually went to Rice University because I wanted to do the experiment myself because I was fascinated. But it's also probably worth pointing out that there's a very good half-price bookstore in Houston, which is another reason for going. It wasn't just that I wanted to do the science. I wanted to go to this bookstore, so I had two reasons to go to do it. I think it's important to be aware that I was pretty sure I knew what the answer to the question was going to be. As people say, there's lots of philosophies of science who says you mustn't do something where you know the answer to the question, and in some sense that's true. In this case, I knew the answer to the question. I was absolutely certain that Rick Smalley's apparatus would create these things. I mean, it was a tremendous advance technically because it was the first time you could vaporize refractory materials, which are high temperature. So it was a major technological advance in what we call cluster science. So I knew it, but even if you know the answer, it's probably a little bit of philosophy here. You ought to just check it out for several reasons. The first reason is it might be true and fine, and then you can tell, in my case, your colleagues who didn't believe you, I told you so, all right? You haven't moved on further. You haven't learned anything because although you've learned that you're right, so you've not actually made an advance in your own understanding of nature. You've just confirmed your knowledge, so that's useful, because until you got that confirmation, you don't know that you're right. Important. The second thing about it is that it might go wrong, and it doesn't work, and then you know that your other ideas were not right, and that you've learned something now. So you always learn more from an experiment that goes wrong, than you do from an experiment that goes right, if it goes right according to your hypotheses. So the second one, if it goes wrong, that you're right, and you've got to find out why it goes wrong. Now, it may go wrong because you haven't done it properly, but it may also go wrong because your preconceptions and your received wisdom is incorrect. So you definitely learn something in general there. And the third thing is that it might go right, but something totally unexpected might happen. And of course, that's what happened. In that experiment, something happened that no one predicted. And in a sense, the most important aspect of our discovery is not that this C60 football-shaped molecule can be made, is that it makes itself spontaneously, perhaps more important than anything else, because that was a fundamental paradigm shift in our understanding of carbon and also sheet material. I first suggested the experiment around Easter of 1984, and when I came back to Sussex at some stage, not that long after, maybe in the summer, Tony Stace, one of my colleagues, gave me a paper by a group at Exxon who had actually vaporized carbon. And it was a remarkable paper that they'd seen some very interesting new species, a whole set of carbon clusters from about 30 to 190 maybe, and they were all even. And I looked at this paper and I thought, damn, we could have done this experiment. If only Bob and Rick had listened to me, we could have done that the day I was there. It was a very, very easy experiment. Anyway, I read the paper through, and there were some interesting aspects, and it actually confirmed again more than ever before that the experiment I wanted to do was perfectly feasible. In fact, part of the experiment had been carried out. I feel I should have looked at that in more detail. Anyway, most of the experiment had been carried out, but they hadn't done the reactions with hydrogen and nitrogen that I wanted to do. In our experiments, we carried out some experiments which were really changing the conditions, really pushing this experiment, not just let's do this experiment and then rush to the next one. And we found that the 60 signal could be made extremely strong. I'm sure if Exxon or Bell had persevered and changed the reaction conditions in the way that we did, they would have seen the same result, and they would have discovered C60, because they would have said, gee, this thing is so strong, what structural explanation is there for this strong signal? And they didn't do that, and so I wouldn't be sitting here being asked about it, because they would have discovered it.
One of the offshoots of Dr. Kroto's work was nanotechnology.
I think there's still some major problems to be solved. There's no doubt that the round cages are beautiful, and they've changed our understanding of graphite and how graphite behaves, that it can close up into a cage. The nanotubes, which were discovered by Japanese, Sumio Iijima, are very interesting. These are sort of elongated cages. They bear the same relationship as to a dome or a ball as a tube does to these so-called nanotubes. And they're fascinating, but they can conduct light metals, so they're an inorganic superb conductor. They are extremely strong, probably the strongest materials ever made. But to actually use those properties is a major problem which is yet to be solved and may be quite difficult. I'm a bit apprehensive that the applications of nanotubes and C60 will be in the near future. There's still big technological problems. As ever, there's always the hint of exciting promise, but getting that promise to the marketplace is still...
And finally, Dr. Kroto discusses his philosophy of science and life.
For me, life is a puzzle whenever I'm anywhere, something that I don't understand. I have to find out how it works. As far as science is concerned, I don't think about the big questions at all. I just think about the things that interest me, and even if they're not very exciting, or don't appear very exciting, but interest me, I follow them through. And in fact, the discovery of C60 was such a problem. It wasn't the most exciting problem I could think of. It was interesting for me, but it turned out this big surprise. And so the lesson that I've learned all through my life is that just look at the things that interest you, and just sometimes they may turn out to be incredibly fascinating.
Well, I'm going to close on that note. I want to thank my producer and IT genius, Sid Tepps. When he discovered the buckyball C60, this is what Dr. Kroto said.
Then we realized it was a soccer ball. At that point, I think it must be right. It was just too beautiful to be wrong.
So to close, here's Thelonious Monk playing a little bit of Too Beautiful.